final part of our videos of generalized linear models, and this time we'll do an example of logistic regression and we'll discuss possible interpretation of results of such regression and different application of that model, and also we'll see how to do a grouped regression in such environment. Let's start with our standard approach with a Jupyter notebook with necessary packages. Similarly to our previous example of data of discrete regression, we will be using artificially created data. We'll have 5 predictors and that predict the binary outcome, and for simplicity we'll assume that these data sets correspond to people, and those people will be either left or right-handed, and the coding of left and right-handedness are 1 and 2. We'll use it in order to distinguish 2 groups in our population, and we'll see how we can use this grouping to improve our inference. As usually, we can do some data exploration. We can see that our data are generally either normalized or standardized, with lower bound either next to 0 or up to 1. With here x1 is from -1 to 1, x3 is -1 to 1, x2 is 0, 1, x4 is 0 to 0 to 1, and x5 is 0 is around -1 to 1. It's harder to read because of difficulties in representation. Different representation here. That here is 9 as a leading number. Here 0 as a leading number. As we can see, the outcomes are relatively balanced. We have balance from 1 to around 50%. However, from handedness is not evenly distributed, as there is the mean is 1.47, while which suggests that we have a bit of advantage of people with of right-handed people. Either way, we have 500 samples of such situation. So we'll start again with prior predictive simulation in order to discuss how to choose a prior for logistic regression. So we create a simple prior predictive check model, which will be again using vectorization in order to simulate probabilities of in the Bernoulli distribution, because we will be Bernoulli because of 0-1 distribution. So this is a little trick here that you can see. In the generated quantities block, we have a certain space in it inside the parentheses. What does it mean? It means that those things outside those braces will be saved and exported as generated quantities. However, everything that's inside the braces will exist only locally. So inside this local environment, we can modify outside declared variables, but those that are declared inside the brackets will not be saved. So it will be useful for us because we are interested only in the parameters inside the Bernoulli distribution. So it will be actually the inverse logit of the linear combination of predictors times model parameters plus alpha. So our model is of course a linear model, intercept plus design matrix times vectors of parameters, and we actually will be considering 2 types of priors. First, priors for alpha and beta will be a normal distribution, again as in the previous examples, with sigma provided as the data point in order to avoid recompilation. However, the other prior that we could try is the student T prior, which is suggested in the Stan manual, Stan wiki that you can find on the Stan GitHub project page, and using that we can compare how those priors look like, because we don't know much about data. Our data are generally either standardized or normalized, so we can try those off-the-shelf priors and see how they operate. So we'll have two models which we have compiled, and those models will be provided with the same data and simulated in an analogous way. In loop, we will be changing sigmas from 10 to from values 10, 2, and 0.75 to see how such priors will look like, and we will simulate our values of probabilities, which we will then use as on a histogram and see how it will look like. So we have three values, three sigmas, 10, 2, and 0.75, and we tried it in both normal and student T distribution, student T with 5 degrees of freedom. So what we can see here is that with sigma 10 we have a lot of concentration of our result, either to 0 or to 1. Why? Because we have a large spread of beta coefficients, and we land in a situation, places where logit function becomes saturated. If we reduce the standard deviation, we get very similar result with a bit of more mass concentrated in the middle for normal distribution. It is kinda acceptable prior because we still allows us theta's for all the areas inside, but if we go with beta even lower, with lower standard deviation of 0.75 for all betas and also alphas, we get all the concentration in the middle, with student T allowing a bit more concentration to the edges, while normal distribution locates almost everything inside, which might be reasonable because looking on the data, we've seen that we have around 50-50 distribution of our outputs. So we looking for values of estimated here might not be such a bad idea. So completing that, we can start doing our model. Our model will be, of course, provided with a number of observation, number of covariates, our design metrics, our outputs, and additionally we'll provide it with information about how many groups of hands is here, so our left-handed and right-handed. We are not considering ambidextrous people, for example, and we provide the vector of hands assignment. So why we will be doing that? We will be doing that for visualization of our data, at least at the moment. We have again two vector of parameters beta, and we have the intercept alpha, and we add a bit of for vectorization to help us later. Our model consists of normal 0.75 priors for beta and alpha from the reasons that we listed above, and we can we will be doing fitting for of our outputs. We're using Bernoulli logit function. Bernoulli logit function is generally a wrapper for Bernoulli distribution and logit function. However, this one is much better suited for computation because there certain shortcuts are being made there to avoid replication of certain steps, and it helps for the derivative computation using automatic differentiation. So that's why such function can be used. However, we'll be doing a bit more complicated approach when simulating the generated quantities, because we will be doing two things. We will try to consider two applications of logistic model. First one is the estimator of population parameters. This is, for example, useful for elections, when we have an election and we want to estimate which candidate is more preferred by population. Using such situation, we will be interested in generally average probabilities of in a group. And what we will be doing here, we will be simulating the probable we will be simulating the results depending uh, on our theta parameters, and using that we will be able to determine which probability is useful for us in this case. And for this simulation, we will be doing the and for this I had to update the code because it was an older version. We will be simulating these results, and then we will compute the so-called empirical probabilities. These empirical probabilities will actually be the ratios of how many ones to total trials in this version. In our case, 500. So for each of the samples from our Monte Carlo distribution, we will have three numbers: the probability of y equal to 1 for entire group and for left and right hand. Additionally, we will also generate the vector of parameters for each of those in order to be able to see how well our model is predicting the probability of belonging to certain group for each of individual measurement sets. So on one hand, that we are estimating the population parameters. On the other side, we are doing the classification task. So we are seeing how well our model classifies. But in this case, classification looks more like estimating the probability of belonging to a certain class, either to 0 or to 1. So our model is compiled. We feed it appropriate data as required by the data specification, and from the result we can see that we get the parameters certain kind of normally distributed, at least mostly symmetrically. The values are around. Some of those values have determined signs. So for example, here we have values from 0 to 1.5, and so this is generally positive value. Others are not that specific. Again, alpha is relatively close to 0. There is a bit of uncertainty on beta 2, beta 3, and beta 4, and especially on beta 2 and beta 3, because most of our mass includes 0, so we are not sure is the positive or negative effect in those cases. Either way, we can look at the group parameters, and looking from that we can see how our approximated empirical probability looks like. So how the ratio of populations, and as we can see, the ratio that we obtain is rather consistent with average for the entire population. When we computed the average of how many Y's there were equal to 1, we get the, as you can see, we get 0.49. So this is very consistent with our model. Our model generated the values located in this way. However, when we look at the groups, as we can see, while the entire population is well fit, each of the groups is off. Their estimate of their parameters, their probability for each group of obtaining 1 is estimated as around in the middle, but actual for left-handed and right-handed, those results are completely different. And if we look at the individual predictions, so how we look at each of the models, the situation is similar. Here we have a plot where I've sorted all the values by median, and we're looking at the confidence interval for the estimated probability of belonging to class 1 for each of the data points. As you can see, it's relatively well mixed, so we do not have the good classification out. We have the error bars of our coefficients. The error bars are from 25th to the 75th interval with the median inside of it. So generally, our model, while captured well the entire populations, then this has ignored the effects that we actually didn't include in the model. And we will be including those parameters in the model through so-called grouping variables, because we will be in our model we will focus on using the different intercepts for different handlers groups. So generally, it will mean that for zero values of all the predictors, the mean for each of those groups will be different. So what we did here is that we actually, with the same priors for alpha and beta, however, we've added additionally that our coefficients alpha also come from a vector, and this vector will be in this case 2 elements, and we'll have specialized intercept for each of groups. And while we have the same betas for all groups, which is not obligatory, we could also be changing that, we will be just we're calling x times beta, but alpha from hand. Hand is specified as 1 or 2. Tables in stan are iterating from 1. So it is a convenient situation that our numbers from the our numbers from the handless assignment will be providing us appropriate values of alpha for each of model coefficients. Again, we do the same situation. Our expression for probability is a bit more complicated because we have to split the values from left and right-handed in order to be able to add to them and generate an appropriate vector. So we have very similar situations. So what we are doing now, we will be seeing how by changing the handlers we have added additional parameter to our model. So we have different intercepts for alpha and beta, and as you can see, when we have previously we have a bit of ambiguity from alpha. Alpha was a very small value, some of it might be even negative or a bit positive. Now when we had separate alphas and alpha from left and right, we see that for left-handed alpha is positive and for right-handed alpha is negative. So we have significant change in the values of coefficients. And how it will correspond to our group assignment? It corresponds very well. Our model now recognizes each group because it has different intercepts which move the probability from one to another. And that, on the other hand, is very important when considering the individual predictions. By changing the model that considers both groups, which can be interpreted either as categorical variable or as a group variable, splitting it as group variables gives us the possibility to see that for low probabilities we have black values, and for good probability, high probabilities we have the white values. And as you can see, we have also a bit of spread between both of those those lines. Again, as previously, they are sorted by median, so that's why they are so close to each other. But and we can now see how uncertainty works. And even in this 50% uncertainty interval, we can see that as they are strictly disjoint the groups between those that are estimated for lower for zero values and for positive values. So here again we have a spread. Selection of assignment is more debatable, requires more tests, but that's a general idea. So what we should remember from this situation, we should remember how to select priors for logistic regression knowing the predictor values, and we should take it that we can either use logistic regression as a method of estimating group parameters, and we can, for example, use it to predict election outcome, or we can use it in a classifier form that will focus on each of the data points and try to assign the probability to it and see how this probability works well. Both approaches have the merits, both approaches can be used. Of course, in technical sciences we are often more interested in diagnostic than especially social predictions, but one needs to have an open mind. Either way, thank you very much for listening. This was the third part on general linear models. Hopefully it was interesting for you. Thank you very much and